Okay, in the previous videos where I dealt with thermodynamics, the calorimetry, the calculation of delta S and delta G, and we talked about spontaneous reactions versus non-spontaneous reactions. Um, I think that I didn't really deal with sort of the big picture view of delta G. So the purpose of this video is to look at four cases where the delta H, which is the enthalpy of a reaction, and the delta S, which is the measure of disorder that either increases or decreases for a reaction, how those two things conspire to determine a delta G, which gives us a basic idea of whether or not a reaction is going to be spontaneous or non-spontaneous in the direction that it is written. Now, what does the word spontaneous and non-spontaneous mean? The delta G essentially gives us two pieces of information. It gives us a sign and it gives us a magnitude. And what that sign and magnitude tells us is the degree in which that process or chemical reaction is going to occur. And the degree at which that process or chemical reaction occurs is going to translate into the amount, the mole amount and gram amount of products produced in the process or in the chemical reaction. So you can think of free energy or the free energy change of a process or a reaction to be a number line. And in the middle of that number line, we have the value 0, which is essentially the equilibrium point of a chemical reaction. And to either side of that equilibrium point, we have delta G's that are either positive or they're negative. All right. So if we have a negative sign, that means that the process in the direction it's written is going to be spontaneous. If the sign is positive, that means the process is going to be non-spontaneous. One must definitely pay attention to the magnitude of the number, all right, the size of the number, because the bigger the number, so for example, if we had a negative delta G and it was a very large number, that means that that particular process or reaction is going to be very spontaneous. It's going to produce a lot of product, large gram amounts, large mole amounts. If the process has a positive sign and and a large magnitude, then what that means is that that reaction is going to produce very, very small amounts of products, very small mole amounts, very small gram amounts. All right, so there are basically going to be four cases that we need to deal with. And in case number one, this is going to be the situation where we have a large negative delta H and a large positive delta S. An example of this is a chemical reaction we've already dealt with. Would be the reaction of propane, for example, with oxygen to produce carbon dioxide and water. All right. Now, in this reaction, you can, this is one of the types of reactions that you can actually predict the delta S of the system because you can count the gas particles. So we have 6 gas particles on this side, and on this side of the arrow, on the right side of the arrow, we have 7 particles. And so we know the delta S for this is going to be positive. If we look, which is favorable, right, because we're moving towards more disorder. Now, if we look at the equation, delta G naught is equal to delta H naught, and we simply enter in the sign of each of the values. For the delta H, there's going to be a negative, and for the delta S, there's going to be a positive, right? Because this value is increasing. The general disorder of this reaction is increasing. And the reaction is highly exothermic. So if I drew myself a picture of a calorimeter here, insulated coffee cup, thermometer, water, this is the surroundings. And we just draw in a box that represents the system. For this one, the delta H is moving from the system into the surroundings. So just reminding the viewer that we also know something about the delta S of the surroundings here. It's going to have to increase because energy is moving from the system into the surroundings. All right, so coming back to the equation, you can see then, just simply looking at the math, that this difference is always going to be negative. So this particular case is going to have a negative delta G naught at all temperatures. All right, now moving on to case number 2. All right, now in case number 2, what we're going to be looking at is when we have a positive delta H naught and a positive delta S naught. And the model reaction we're going to use for this one also is one that we've dealt with before in previous videos, and that's going to be the formation of a solution with ammonium nitrate. And we produce 2 ions here. We know that the reaction is spontaneous based on observation, literally. And in this case, if we look at our formula, all right, and we go ahead and we insert the signs. So for this one, it's an endothermic reaction, and that means heat energy is going to be moving from the surroundings into our system. The delta S naught for this reaction is positive, so there is a gain in disorder going across here, which is really good news. But notice that our delta H naught, which is the enthalpy, is a positive value. So that means we have issues going on with the temperature. All right, and so let's just talk about what can happen with the temperature. Since the delta S is positive here, and we have essentially a minus sign here, this is the same thing as saying plus -1 times this product. This end of our difference is always going to be negative, but the magnitude of the negativity is going to depend on what the temperature is. So we would predict at high temperatures, at high T, that the delta G is going to be also a negative value because this product is able to overcome the magnitude of the delta H here and make this value negative. Now, where this particular reaction is going to run into trouble is if the temperature is reduced. If we begin to decrease this temperature, then eventually this product is not going to have enough magnitude. It won't be large enough to overcome the endothermic quantity that it's being added to, which is going to cause the delta G to move on this number line into the positive realm. So at lower temperatures, the delta G for this is going to be positive, and as a result, non-spontaneous. Now, case number 3. Okay, so case number 3 is going to be where we have, again, an endothermic reaction. So a positive delta H. And we have a negative delta S naught. And the model equation that we're going to use here is the conversion of oxygen to ozone. All right, and notice that the delta S naught of the system is unfavorable. And when you look at the equation, you can see why. Again, it's composed entirely of gases, so we can count particles. And on this side of the arrow, on the left side of the arrow, there's 3. And on the right side of the arrow, we have 2 particles. So we've actually decreased the number of gas particles here. So if we look at our formula, our equation, delta G naught is equal to delta H naught minus T delta S naught. All right, now, and we put in our sign, so this is endothermic, a reaction, so there's the positive sign. And then over here, the delta S is negative. So check out the consequences of this. Remember that we have a subtraction sign here, which is the same thing as saying that delta H naught plus a -1 times what the value is for the delta S naught, which happens to be negative. So this kind of transition is literally in trouble. It's going to be, this particular transition is going to have a positive delta G naught at all t. So this basic process, the way it's written, is non-spontaneous at all t. Okay, this one is not good. Now, let's look at the last case, case number 4, and that's where we're going to have, again, an exothermic reaction. So delta H naught is negative. So energy is being released by the system into the surroundings. All right, and then we're also going to have a negative delta S naught. And the transition we're looking at here will be a phase change, where we take water, which is a liquid, and we convert it into water, which is a solid. So we're making ice, and in order to do that, we have to abstract or remove energy out of our system, and we have to form a crystal. So the entropy here is for the system is not going to be good. But remember something. This is exothermic. So energy is moving from the system into the surroundings, and that tells you that delta S of the surroundings will be favorable because the surroundings is getting an input of energy. What are the consequences, therefore, for the delta G naught? So if we look at our delta G naught, at our equation again, it's going to be delta H naught minus T delta S naught. All right, now let's put in our signs. It's going to be negative for the delta H, and the delta S is negative. Now, again, dealing with the subtraction, all right, this is plus -1 times this product. So this reaction, or this process actually, to be more correct, is going to have a temperature dependence. And the dependence is going to look like this. Where we have low temperatures, all right, low temperatures, think about what that means. So this value right here is going to be small. And when it's small, literally this positive product, when added to the delta H, will not be able to overcome the large negative magnitude of this number, and therefore delta G is going to remain also negative. So for low T, we're going to have negative delta G naughts. That's how come ice freezes when you put it in a freezer. All right, which means that for low T's, this is going to be spontaneous. Low T's, spontaneous. Now, the opposite is true if we increase the temperature. So if we take this number, okay, and we begin to increase it, What it's going to do to this product is it's going to make it bigger. And since we're subtracting a negative, so essentially that says the same thing as plus a -1 times a negative, which is a positive. As we increase the temperature, this product, the positive magnitude of this product, eventually is going to overcome the energy that's being released from the system, which drives the delta S of the surroundings, and it's going to make the delta G positive. So the consequence of high temperature is going to be a positive delta G naught, and as a result, at high temperatures, this process is going to be non-spontaneous. And if you think about this for a minute, it makes perfect sense, because if you take an ice cube out of your freezer and set it on your dining room table, common sense says the ice cube is going to melt.